use Stokes Theorem to evaluate the surface integral, where we have a vector field defined as z squared minus 1 I hat plus z plus xy cubed j hat plus 6k hat, and S is the portion of the surface, x is equal to 6 minus 4y squared minus 4z squared, in front of x equals negative 2, with orientation in the negative x direction. So, what is going on? Let's think about what the sketch looks like. So we know that we are in space. We have our z-axis, we have the x-axis, and the y-axis. And we know that our surface here is the portion of the surface where we have a paraboloid. So we have a paraboloid with a vertice at 6. Say right about there is 6. And so here is our paraboloid, the portion of this paraboloid, opening towards that the negative x-axis. And then this paraboloid is in front of the plane at x equals negative 2. So we'll say there's negative 2, and it's intersecting with our paraboloid. So that's our curve C, and this whole thing is our surface S. So let's think about, we'll shade this in so we can see our surface. So here is the surface intersecting with that plane. Beautiful. Now, we also want to think about our region of integration here. And we can actually see that it's slightly different because our region of integration is at the plane. And this is the plane defined as x equals negative 2. And we also have our paraboloid explicitly defined as x is equal to 6 minus 4y squared minus 4z squared. Ooh, before we look at our region of integration, you also want to keep in mind that this orientation of the surface is in the negative x direction. So that means its orientation is moving in a clockwise direction. All right, so we are ready now to think about our region of integration. What does this look like in the plane? So since we have two surfaces here that are intersecting, to find our region of integration, we need to equate our surfaces. So we want to equate the surfaces. So in other words, since x equals x, we know that we're going to have negative 2 is equal to 6 minus 4y squared minus 4z squared. And we want to solve this. So bringing all of our terms to one side, so this will give us minus 8 is equal to negative 4y squared minus 4z squared. And we can divide both sides here by 4. So this leaves us with something that we recognize. We have 2 is equal to y squared plus z squared. So our region R in the plane is a circle centered at the origin with a radius of the square root of 2. So to help us in determining our bounds and parameters, if we want, let's actually think about this sketch real quick. So we have our y and z axes here. So we'll say this is y and this is z. But if you labeled them in the reverse, that's fine too, as long as you're labeling. And so here is our curve C. It is oriented in a clockwise direction. And we're thinking about the region within this. So there is our region R. And we have two options here. Oh, don't forget to label. So we got the square root of 2, that's our radius. So if you were going to use a surface integral, so I'll abbreviate surface integral, this is a perfect polar region, so we would use polar bounds. And we can say that our radius r is greater than or equal to 0, less than or equal to the square root of 2. And since it's a complete circle, theta is greater than or equal to 0, less than or equal to 2 pi. Now what about if we were going to use a line integral? So I'll abbreviate line integral. Well, we would need a one parameter description for this region. So we could say that x of t is equal to -2. And why, you might be asking? Well, don't forget that this curve, if we look back up at our three-dimensional sketch here, this curve is in the plane x equals -2. So this is because C is in the plane x equals -2. So the one parameter description for the y coordinate is the square root of 2 sine of t. And then we're treating z here like it's the x-axis. So we can say that z of t is equal to the square root of 2 cosine of t. And this would all be such that t is greater than or equal to 0, less than or equal to 2 pi. So let's use the surface integral here for good practice. But this parameterization here is also going to come in handy later in our integration. And I challenge you to try integrating this both ways to make sure you're getting the same answer. And my last love note before we actually look at evaluating this surface integral is that this parameterization here is not exclusive. Other parameterizations do exist. So it all depends on how you're thinking about this region. Alrighty, so again, we have selected to evaluate this using the surface integral of Stokes' theorem. So that's the double integral over the surface S of the curl of the vector field dotted with the normal vector ds. So let's go ahead and find the curl. And again, we were given the vector field defined by the components z squared minus 1, z plus xy cubed, 6. And we want to compute the curl. So we know that that is the del operator crossed with the vector field. So we'll use our 3 by 3 determinant here. We have I hat, j hat, k hat. The second row is the components of our del operator, ddx, ddy, and ddz. And the third row is the components of the vector field. So we have z squared minus 1, z plus xy cubed, 6. And by the cross product, we are left with 0 minus 1 I hat minus 0 minus 2z j hat plus y cubed minus 0 k hat. So we can say, therefore, the curl of our vector field is defined as minus I hat plus 2z j hat plus y cubed k hat. And we can put that into our component form, minus 1 2z y cubed. So now that we have the curl of the vector field, we need to go ahead and find a normal vector. So a fun alternative to our right-hand rule is to recall the following. So let's recall that the gradient vector, del f, is normal to the surface f at some point. So the gradient vector is normal or perpendicular to the surface f, say of x, y, z, at some point x, y, z. So we can use the gradient to find a vector normal to our surface. So let's think about what we are given. So we know to start, we have this surface defined by the paraboloid x is equal to 6 minus 4y squared minus 4z squared. So we have an explicitly defined surface here. So we can say that this is equivalent to x is equal to g of yz, where g of yz is defined as 6 minus 4y squared minus 4z squared. So if we know we want to take the gradient or find the gradient vector to this surface, we want to rewrite this surface implicitly. So we can say that a implicitly defined surface f of xyz is equal to x minus g of yz. So this would be equal to x minus 6 plus 4y squared plus 4z squared. And we'll use this implicitly defined surface here to find the components of the gradient. So we need the partial derivatives. So we need the partial derivative of the surface with respect to x, which leaves us with 1. We have the partial derivative of the surface with respect to y, which leaves us with 8y. And we need the partial derivative of the surface with respect to z, which leaves us with 8z. So therefore, the gradient of this surface is defined as the vector with components 1, 8y, 8z. But you want to exercise caution here. We want to keep in mind the orientation of the surface. So since S, our surface, is oriented in the negative x direction, we want to think about the negative version of this. So since S is oriented in the negative x direction, we take the normal vector to be the following. So we take our normal vector n to be minus the gradient of f. So this leaves us with the vector minus 1, negative 8y, negative 8z. So this adding of the negative here takes into consideration that our surface is oriented in the negative x direction. So we have all the pieces and we're ready to set up our surface integral. So here we go. We are ready to evaluate the surface integral. So we have the double integral over the surface S of the curl of the vector field dotted with the normal vector integrated with respect to the surface. So plugging in those bounds, again we have the polar bound, so this is from 0 to 2 pi for the bounds on theta. We have 0 to the square root of 2 for the bounds on the radius. We know that the curl of our vector field is minus 1 2z y cubed, and this is dotted with that normal vector in the negative x direction. So it's minus 1 minus 8y minus 8z. And then don't forget, because we're integrating with respect to our polar coordinates, this we'll have the differential r dr d theta. All right, so let's compute that dot product. So we have the double integral from 0 to 2 pi, the inner integral from 0 to the square root of 2, and by our dot product here, we are left with 1 minus 16yz, and then minus 8y cubed z. And that's r dr d theta. So, looking at our differential here, we see we should only have the variables r and theta. However, looking in our integrand here, we realize we have y's and z's. So we need to fix this by thinking about those polar coordinate conversions. So let's quickly recall our polar coordinate conversion so that we can convert y and z to r and theta, or polar coordinates. So I want you to keep in mind here, we're treating z like x. So we are treating z like x. If we think back to our two-dimensional sketch here, we have that y and z axis in the plane. So bipolar coordinates, we know right off the bat that y is certainly going to be equal to the radius times sine of theta. And so if z is acting like x, we know that z will be equal to r times cosine of theta. And so we can plug these in to our integrand and simplify. So this will become, let's actually give ourselves more room. So here we go. This is the integral from 0 to 2 pi. The inner integral is from 0 to the square root of 2. And this is now of 1 minus 16. So we have r sine of theta times r cos of theta. So it'll be 16 r squared sine of theta cosine of theta. And this will be minus 8. And we have y cubed. So that's going to be r sine of theta cubed. So r cubed times sine of theta cubed multiplied by r times cosine of theta. So that means we have 4 radii together. So that's going to be r to the 4th multiplied by sine of theta cubed times cosine of theta. And then don't forget your differential r dr d theta. And so before we start integrating, let's make some observations here. Notice with this first term, because eventually we're going to need to integrate with respect to theta, we actually have a double angle formula in here. You can see if we have 16 sine of theta cosine of theta, that's equivalent to saying 8 multiplied by 2 sine of theta cosine of theta. And we can see our beautiful double angle formula there. So let's rewrite this. We have the double integral with the outer bounds 0 to 2 pi. We have the inner integral is from 0 to the square root of 2. So our integrand is now 1 minus 8r squared times sine of 2 theta by that double angle formula minus 8r to the 4th sine cubed of theta multiplied by cosine of theta multiplied by r dr d theta. So before we integrate here, let's be mindful that we need to distribute this radius through to each part. And don't forget that 1. So we are now left with the double integral. We have the outer bounds are 0 to 2 pi. The inner integral is 0 to the square root of 2. Now we have r minus 8r cubed sine of 2 theta minus 8r to the 5th sine cubed of theta cosine of theta dr d theta. And we're ready to integrate. So giving ourselves a little bit more room. So we're just integrating our inner integral here. So the outer bounds stay as they are, 0 to 2 pi. Integrating with respect to r, we now have r squared by 2 minus 2r to the 4th sine of 2 theta minus 2/3 r to the 6th sine cubed of theta cosine of theta d theta. And don't forget, we need to evaluate now from 0 to the square root of 2. So plugging in those bounds, we have the outer integral is still from 0 to 2 pi. Now we're evaluating at the square root of 2 first. So we have the square root of 2 squared will leave us with 2 over 2 minus 2. And then we have the square root of 2 to the 4th. So that gives us 4 times sine of 2 theta. This will be minus 2/3. Then we have the square root of 2 to the 6th. So that will be 8 times sine of theta cubed cosine of theta. And then fortunately when we plug 0 in, everything goes to 0. And so simplifying, we have the integral from 0 to 2 pi of 1 minus 8 sine of 2 theta. We have minus 16/3 sine cubed of theta cosine of theta d theta. And so we're ready now to go ahead and integrate this with respect to theta. So the first two parts are just general antiderivatives. So this will integrate to theta. Then we have plus 4 cosine of 2 theta. And then with the second part, I'm just going to distribute our integral through to it. So this will be minus 16/3 times the integral from 0 to 2 pi of sine of theta cubed times cosine of theta d theta. And the reason I'm doing this is that we need to use u substitution here. So let's just step to the side and think about the u substitution associated with this third portion of our integral. So looking at the integrand, I'm going to go ahead and let u be sine of theta. So then du d theta gives us cosine of theta, and we want to solve for that differential d theta. So we're left with du by cosine of theta is equal to d theta. So this is the substitution portion that we're plugging in again to that integrand. So continuing with this, we have now minus 16/3 times the integral from u of 0 to u of 2 pi. Again, plugging our substitutions in, we end up with u cubed du. And so this integrates to negative 16/3 multiplied by u to the 4th by 4 from u of 0 to u of 2 pi. And of course, we can simplify that to minus 4/3 u to the 4th, u of 0 to u of 2 pi. And normally I would change the bounds, but keep in mind that we still have theta and 4 cosine of 2 theta to evaluate from 0 to 2 pi. So I left the bounds as they were. Just be sure to protect those bounds with u, because the variables are different. So let's plug this back in, replacing the u with the original sine of theta. So the whole integrand is now, or antiderivative, is now theta plus 4 cosine of 2 theta. And now we have minus 4/3 times sine of theta to the 4th. And now we are ready to evaluate from 0 to 2 pi. So let's go for it. So plugging in 2 pi first, we have 2 pi plus 4 cosine of 4 pi, which is 2 times 2 pi, minus 4/3 sine of 2 pi to the 4th. And then we want to subtract the evaluation at 0. So this will be 0 plus 4 cosine of 0 minus 4/3 sine of 0 to the 4th. And we have some lovely simplification here. We know cosine of 4 pi, of course, goes to 1. Sine of 2 pi, of course, goes to 0. Cosine of 0 goes to 1. And sine of 0 goes to 0, which leaves us with 2 pi plus 4 minus 4 for a beautiful final answer here of 2 pi. So therefore, we have shown Stokes' theorem, the double integral over this surface of the curl of our vector field dotted with the normal vector to the surface, integrated with respect to our surface, is 2 pi.